We're live.
Hello world, it's Siraj. We started a little late because I was having some Tensorboard trouble, which I still am having, but it's all good because when I say I'm gonna go live, I'm gonna go live. So today we are going to talk about Tensorboard. So Tensorboard is the tool that comes with Tensorflow, so it's built in. So if you've installed Tensorflow, Tensorboard comes with it. And the goal of Tensorboard is to help you visualize your data. It can help you optimize your data, it can help you debug it, it can help you look at ways that you can improve it, and there's also the plugins feature which is coming soon, so I can't wait for that. But yeah, it's a pretty cool tool, and I admit I haven't used it much, and that's because I think the use case for it really shows itself when your data starts to get really complex. That is your models. So when your models start to get really big, that's when Tensorboard becomes very useful. And one of the reasons I'm demoing it now, so I already made a video on Tensorboard before, but one of the reasons I'm doing one again is because the embedding visualizer is a pretty cool tool, and I'd love to talk about that. And it's a new tool. And it's going to be really cool. So in this demo, what we're going to do is we're going to look at MNIST. Now, I know you guys have seen MNIST a million and one times, but the point of this is not MNIST, it's the embedding visualizer specifically. So that's what we're going to look at. And so yeah, I'm going to start off by showing the code that we're going to use, and then we're going to visualize it in Tensorboard, and then we're going to look at the details for each of the sessions. All right, so let me start off by looking at the code here. So what I'm going to do is I'm going to explain the code, and then we're going to go into the session itself, okay, or the code itself. All right, so to start off with, let me remove some things. So to start off with, we're going to look at this code. So I've got it up here. I want you guys to download the code and follow along with me, okay? So what this code does is it is a convolutional network. It's a convolutional net, and it is meant to classify handwritten characters, okay? So let's look at what it is, and let me start off with a 2-minute Q&A, okay? So go ahead and ask questions, and yeah, it's gonna be awesome. Hold on. We got code, we got questions, we got Sublime, we got audio lag. Yeah, all the things are here.
Audio lag should go in a second.
We are all tensors. Okay. Any questions, guys, before I get started? Because I'm about to go in on this, no pun intended. Okay. How do we decide the topology of a neural network? Great question. So many decisions go into that depending on your use case, what you're trying to do. But I would say there are a few general rules to go by, rules of thumb. One would be the more layers, the more computation, but also the more accuracy your model will have. What type of network? It depends on your use case. Convolutional network for images, recurrent network for time series data, feed-forward network for binary data, and then more complex data, there are different types of models. 2 more questions, and then we're going to get started. Audio is a little low. We'll take care of that. How to use Tensorboard with Floyd Hub. I haven't heard of Floyd Hub. Actually, I've heard the term, but I don't know what Floyd Hub is. How much product goes into that hair? So surprisingly, none. It's just I just roll out of bed and I do this. One more question, not about my hair. How do we use Tensorboard with AWS servers? Now that's a great question. So I actually have not seen that done before. Using Tensorboard in the cloud would be a good idea if you had, if you were using transfer learning. So if you were using a model that you yourself hadn't trained and it's a huge model, then using it without having to download it directly from the web would be, actually that'd be a great startup idea. So not just AWS, but just visual. So here's a great startup idea for you guys. Visualizing modeled architecture in the web is a problem that has not been tackled at all. Right now we have to do this locally and no one wants to have to do that. So great, that would be a great problem. Okay, so let's go into the code. Okay guys? So what I'm gonna do is I'm not gonna type out the code, I'm gonna talk about it, and then we're going to look at the Tensorboard. Then we're going to look at the Tensorboard version. Okay, so to start off with, let me maximize this code so we have a good look at it. Okay, let's maximize. So here are libraries, okay, and then for URL lib, I have this little versioning because for Python 3 versus Python 2, URL lib is annoying, so we have to have this. And so then these two constants, these constant values, are what we are doing here. And so this is the novel part, is we are importing the embeddings from the web. So let's look at what this link is. So on GitHub, if we look at this link, we can see that it's an invalid request. That's what we can see. But there's also, let's see. So, okay, hold on. Okay. So here's what we're pulling. We are pulling these. So what are these? So I actually have these locally, so let me just open them locally. So there are two things here that we are pulling. The first is a collection of sprites. So these are sprites. So what are these? So what we are doing is we are classifying handwritten characters. Now, most of us are familiar with this example, but this is novel. So for the embedding visualizer, which is a new feature of Tensorboard, we can visualize the learned vectors that our model creates when training on our input data and input labels. So we have characters, right, 1 through 9. And these are what are considered sprites. So when we learn these mappings from our model, when our model is training, it's learning what a 7 is. It's learning and these vectors represent the correlation between the actual number, the number 7, and the image of 7. And that correlation is represented as a vector. So the way that we can then represent that vector is to have a sprite. And these are the sprites. And so this image is going to be cut into squares. Okay, so starting from the top left to the bottom right, we can think of it as a matrix. And when we visualize it in Tensorboard, these sprites are going to show up as the images for what we've just visualized. Okay, so just like this. I'm doing this because I haven't actually launched Tensorboard yet, but it would look like this, right? So see these 4s and the 0s? Those are the sprites. Those are values that are coming directly from this sprite file. And then associated with that, we also have let me see, where did I put this? A labels file, which is a TSV file. Okay, so the labels file is it's a file extension for tab delimited. It's like for spreadsheets. So it's imported into and exported from spreadsheet software. And these are just the associated numbers. These are the associated numbers. It's such a weird format, but every single number associates with one of these images from this matrix right here. Okay, so each number is associated. So that's what we're doing. Okay. Okay, so that's what that is. Let's keep going here. So the next part is for us to download these embeddings. So what this line does is it is downloading the MNIST data, and it's splitting it into 3 parts. You have 55,000 data points of training data, 10,000 points of testing data, and then 5,000 points of validation data. And so we're going to call the images X, and we're going to call the labels Y. And each image is 28 by 28 pixels. Okay, so these are each of these images. And that's what the read datasets function is doing, having downloaded that from the web. Okay, and we're going to store that in MNIST, the variable. Okay, so let me increase the font size a little bit. Okay, so now that we've done that, we're going to define our layers. So we have convolutional layers. Okay, so for our convolutional layers, let's talk about what's happening here. So in a standard convolutional network, we have 3 layers. And I'm going to answer questions in 20-minute intervals. So in 7 minutes, I'll start answering questions. But let's look at this architecture right here. So I think Inception is a good example, convolutional net. All right. So in standard convolutional networks, we have what are considered blocks. Okay, so it doesn't matter what these words say, but we can just think of these as blocks. Okay, so this is actually a huge convolutional net, probably one of the biggest in the world. But the point is that we have a convolutional layer, and in each of these blocks, we have three things. We have an input. So typically, a CNN is composed of a stack of convolutional modules that perform feature extraction. So each of those modules consists of a pooling layer. It's got and then a fully connected layer, and then a what's the next one? And then a softmax activation function. So we squash it. So we just keep doing that every time. Okay, so we're going to define that programmatically here. So let's go ahead and do that. So the first line here is the name scope. So in Tensorboard we have name scopes, right? So name scopes basically define. So this one's not working. So right now we're going to look at Tensorboard in a second, but right now let's look at the name scope feature. So there are so many variables. There's so many tensors. There's so many components to a computation graph. So what name scopes do is they're a way for us to encapsulate all of that complexity under one name so that it's easier for us to view in the graph. Okay? It's easier for us to view in the graph. So in this case, we're using a name scope, and we're going to define it when we call this function. But the name scope itself is going to encapsulate the weights and biases and the convolutional part, the activation part, and then the pooling part of this convolutional, which we can call a block. Okay, so a convolutional block consisting of these three layers of pooling, of an activation function, and the weights and biases. So it's all going to be encapsulated, and we're going to see that in Tensorboard when we visualize it in a second. Okay, so a TF variable maintains the state of the graph. Okay, so that's what we're using variable for. And truncated normal is going to output the random values from a truncated normal distribution. And so then the constant is going to create a constant tensor. Okay, so those are our weights and our biases. This is going to be for our first convolutional block. Okay, and then we're going to compute a 2D convolution given a 4D input. That is the 4D tensor that is coming directly from the placeholder that we're going to define later. So right when we input data into our model, it's going to go right into this convolutional block. Okay, and then once we have that, we're going to create what are called histograms. So let's talk about TF summaries for a second. So what are these summaries and why do we use them? So a summary is a TensorFlow operation that outputs protocol buffers. So protocol buffers are a way of encoding data. So it's serializing the data that we have in memory to disk. So we're writing it to disk so that we can then pull it in Tensorboard and visualize it. So that's what the TF summary function does, and there are different things that we can use summaries for. So in Tensorboard, we have different types of summaries, and we can see what types they are by looking at the tabs up here. So we have summaries for scalars, for images, audios, graphs, distributions, histograms, and embeddings. So we have different summaries for both, and we'll talk about when we use those summaries and why we use them. But for this case, we're going to use histogram summaries because we want to see a distribution of values across the weights, biases, and activations. Okay, because we're randomly initializing these values right now, right, with this truncated normal function. And as we update those values over time, there's going to be a distribution of possibilities, and we want to show what they actually are, and then also what they could be. So then that's useful for debugging. So we could then rerun our model with a different set of hyperparameters and see how those distributions move. So that's what this function is, and then we have a max pooling. We have a max pooling layer, which pooling in general is really cool. So pooling, there's so many different types of pooling methods that we could use, and max pooling seems to be the one that's used most often. So for max pooling, let's say we have a 4x4 matrix, right? We have a 4x4 matrix, and that is our input image. And we have a 2x2 filter. So the reason it's called convolutional is because we are taking a filter, which is kind of like a flashlight, and we are convolving around an image, and we're only using the parts of it that we find relevant. So it's like it's like taking a flashlight to an image and looking at what those relevant features are. And there are also these, there's another parameter called strides, which are essentially intervals. So at what interval do we want to look at the part of the image we're looking at? Every 2 pixels, every 4 pixels, every 8 pixels. And depending on what your stride length is, we need to tune that so that our model is better or worse. And we can do that through trial and error. And what pooling is it says, let's take the max of a region and just use that as the input. So if we had a, let's see, let me show a little image for that and then we'll keep going with this. So this is pooling, right? So this is, if we could look at our image, because images are all matrices, right? Why we use pooling? So images are matrices. An image is a matrix of pixels. So if you think of this image right over, I want to see if I can, there we go. So this image over here, just the big image over there. And then that's our image. So what pooling is it's saying what portion of the image do we want to use when we take that data and pass it forward through the network. And with max pooling, we're going to say, well, if we were to split these up into squares, like 4 different squares, if we were to add up the value in each of these squares, which big square would contain the most values? And that's the max values. And that's the square, the subset that we're going to use. And that's the subset we're going to pass forward in the network. Okay, and pooling is the most popular max pooling is the most popular of the pooling methods. Okay, so that's what we did for one of our layers, and right. So following along, we established our weights and biases. And then our convolutional layer, we applied an activation function to it, and we used ReLU. And so why do we use ReLU? Because ReLU reduces the likelihood of the vanishing gradient, which recall for neural networks, for LSTMs and time series data, the vanishing gradient is a huge problem, and it's also a problem in convolutional networks, okay? So that's that layer. Now we have another layer, and then we're going to get into actually building our model. So this is our fully connected layer. And so what this does is it performs classification. And we use this in all sorts of networks. It's not just fully connected layers are used in almost every type of neural network. And we use them pretty much before we squash it into using an activation function to output a prediction. So fully connected layers are usually found at the end of neural networks. At the very end. And what they do is and the reason that we use fully connected layers is so that we can use all parts of the data because we want to squash it. Okay, so that's what that is, and we're going to do the same thing. We're going to use the histograms to create summaries for the weights, biases, and activations. Okay, so that is that. And so now let's build our model. Okay, so we'll establish our graph and initialize our session. And now we're going to have placeholders and these are going to be the gateways for data. So imagine we haven't done anything. All I've done here is I have talked about what those layers are going to be. And then now we're going to actually initialize them. So let's see if we have any questions, and then we're going to talk about what this looks like. How does max pooling work with an image of only ones and zeros? Oh, that's a good question. So the ones would then, the part of the matrix that has the most ones would then be the pool that we use. That's the max value. 2 more questions, and then we're going to keep going with the model. How did he get those keywords? Okay. If we had infinite resources, we wouldn't do pooling, right? That's a good question. So, yes, the answer is yes. Yeah, I've never thought about it that way. Yeah, because a lot of machine learning is a trade-off between computational complexity and brevity. Brevity be that in code, or brevity be that in training time. Like we want to minimize the training time, minimize the amount of code we have, minimize the computational complexity so that we can maximize our, but also maximize our prediction accuracy. So one more question, and then we're going to get started with this. Does max pooling use a sigmoid function? No, it does not. It does not. Max pooling sigmoid is an activation function. That's not. Max pooling is an operation. Okay, so now to build our model. We have our placeholders for our images, so that's going to be our tensors. And then we're going to use the summary, remember, the summary function of TensorFlow to create a summary protocol buffer for images. So we can visualize these under the images tab right here. We're going to visualize that in the images tab. And then we're going to define our model. So depending on how many layers we want, we have an if-else statement. So if we have 2 layers, then we can use that function we just defined to then call the layer. And then, so if we have 2 layers, then we're going to use that function we called to build a model. Else, we'll just use 1 layer. And then once we have those layers, we're going to, at the end, we're going to flatten it, and then we're going to feed it to a fully connected layer. And we flatten it because it's more computationally efficient for our model to read a one-dimensional tensor than a two-dimensional tensor. However, there are ways of not having to flatten an image and then using that two-dimensional tensor directly. But however, it's more computationally efficient. Complex, not efficient. Okay, so those are our fully connected layers, and those are our convolutional layers. And then we'll take the flattened image and feed it to our fully connected layer. And then we will create those embeddings so that we can visualize them later. So at the once we have those fully connected layers, that's where we're taking our embeddings to visualize. So that's the part where the embedding visualization is going to happen. So data is flowing through our convolutional layers, okay, through the max pooling, through the activation functions. It's getting flattened and then fed into the fully connected layer at the end. And that the result that the fully connected layer creates, that embedding is what we're going to visualize, and it's going to be so dope when we visualize it. It's so cool. Okay, so and I'll answer questions in 5 minutes. So that's what we have for that. And so, and then we're going to take the logits, which is the probabilities that don't equal 1. It's the output. We have the embedding. We stored that in the embedding variable. And now the logits are going to be the output of the fully connected layer. Hey, Alexa.
Computer.
Hey, computer. Do you like TensorFlow? No? It was a little, we had Alexa here, but she didn't work. Anyway, I thought it would be fun. So anyway, so the next step is for us to define our loss function. So we're going to use the standard cross entropy loss function with logits. So the logits are all those values that we output. We squash it, and then that's it. Once we have that, we can then generate our prediction from it. So this output is going to be our set of prediction values, okay, from this namescope, which we call XENT, which is short for cross entropy loss. And the output of this, so XENT, is going to be our loss. And we're going to visualize this loss in TensorBoard as well. So remember, namescopes are going to group operations together so that we can then visualize them as a whole in TensorBoard. Okay, so so now we've defined our model, and now we can train it. So we don't just define namescopes for our model. We also want to define it for our tensors, or so for our training operation and our testing operation. So for our training operation, we're using Atom. And so I've written down a huge explanation here of like why to use Atom and when not to. But in a nutshell, Atom gives us better results than the standard gradient descent optimizer, but it's more computationally complex. So if you're willing to make that trade-off, then I would go for Atom. And most of the papers these days that are using convolutional nets, I tend to see Atom used more often than the standard gradient descent optimizer. But if you're a beginner, then I would go for gradient descent optimizer. Okay? Okay, so, and let me try Alexa one more time. Do you think I should? Yeah. Hey, Alexa, or hey, computer, what day is it today?
Computer, what day is it today?
It's Wednesday, April 5th.
Oh, it doesn't like me, okay.
I think it's the voice.
The voice, okay. So anyway, that works. Anyway, so we have our training, we have our accuracy. So hold on, guys. We're about to visualize this in Tensorboard. I know, I've been waiting for that too. Let's just get through this code, okay? So we have 380 people here from all over the world, okay? We are growing so fast. It's amazing. It is amazing. So I am so honored to be here with you guys. So where were we? We have defined our training function, and now we're going to define the last namescope. This is the last namescope that we're defining here, which is the accuracy. So we're going to take the logits, and then we're going to, which is a collection of the probabilities, and we're going to choose the average, which using the we're going to use argmax, which is going to get the largest value, and then we're going to get the average using the reduce mean function. And accuracy is going to be one scalar value. That is our prediction right there, the accuracy. Okay? My desktop is pretty crowded. It's a lot of editing, but anyway, where was I? Make this bigger. Okay, so now it's time to look at the novel stuff about Tensorboard here. So in a lot of the initial Tensorboard tutorials, it didn't have this because the embedding visualizer didn't exist, but now it does. So what we're going to do is we're going to, the reason we summarize the reason we merge the summaries before we write to disk is because it's more computationally efficient. Instead of continuously writing them to disk, we just merge them all, and so it's one write versus like 10. Okay? Okay, so where was I? So we did that, and now we're going to initialize our embedding matrix as an array of zeros, and then we're going to assign it the embedding that we just calculated. All right, so now it's in our assignment. Okay, so now it's in our assignment, and now we're going to initialize a saver, and the saver is used to save and restore all of our variables. And so then we're going to initialize the file writer. So we have our summaries, and then we have the file writer. So the summary operation creates the protocol buffers so that we can write it to disk. And the file writer is that method that we are able to actually write to disk. So we create summaries, and then we save them to disk using the file writer. So they both go hand in hand. Okay, so that's why we use the file writer. And so this part needs to be better. Let me just say that. This part needs to be better. So in the initial TensorFlow example, so there actually are not a lot of examples of Tensorboard that use this. That you can look at the embedding visualizer in. There are not a lot of examples of Tensorboard that you can use the embedding visualizer in. So there should be. So this is one of them. So definitely check out the GitHub repo because there are not a lot of them. The problem with this is that it's using the config file directly from TensorFlow. Now, I would like it so that we can define our own configuration file. But if we look at this proto file, let's look at what this looks like. It's pulling it from the web. And so let's look at what this looks like. 404 here. Man, we gotta clean this up. No, it's not this. There it is. So here it is. So these are the options that we're using to build our embedding visualizer. So we have a tensor name, we have metadata, and then we have our project configuration. Okay. So we could also define these locally if we wanted to by creating a protobuf file locally and then calling it from disk. But right now it's calling it from the web right here. Okay. So we could add multiple embeddings, but we're just going to add one, and that's what we've learned from our embedding matrix. Okay. So we have that, and we're going to specify the width and the height of it with a single thumbnail. Okay, and so they're 28 by 28 pixels. Okay, so that's it for that, and then we train it, and then we save the checkpoint every 500 iterations. So this thing is going to run for 2,000 iterations and each batch is going to be 100. And then and so that's what the training step looks like. And then we have our main function where we call it, and then this make hparam string function just converts a hyperparameter string to one that is more detailed for us. It's just for us. Okay, so that's the code. I wanted to kind of blow through it a little fast because I wanted to get to Tensorboard. So before we get to Tensorboard, let me ask if there are any questions before we get started with this. Okay, I'll take 2 questions. And this was working before I started. Oh my God. You guys know how it is with demos. Like, literally, it works perfectly. It worked. You could rerun. I literally stopped it and reran it like 3 times before starting it. Boom, Tensorboard. You know that little command line with Tensorboard? And it was running. And then 5, literally, almost like the gods of deep learning were, of demo hell were there. I should say Satan. They didn't make it go. Or it didn't work. So we're gonna debug it in real time, and let's see if we can make Tensorboard work in real time, okay? So we'll see. So 2 questions. How do you interpret the histograms? I have trouble giving meaning to the axes. That's a great question, and I'm gonna talk about that when we look at it. Are there any third-party wrappers for TensorFlow so as to convert symbolic programming to kind of simulation for end user in object-oriented programming? That is a big question with a lot of parts to it. Third-party wrappers for TensorFlow? Yes, there are. TensorLayer. Look at TensorLayer. Google that. TensorLayer. Are you using GPU version of TensorFlow? Yes, I am. What does protobuf file do? So protocol buffers, Google invented this like a couple years ago, like 6-7 years ago. But basically, protocol buffers are a serialization method. So serializing is a way, like pickling is a form of serialization. It's a way of taking some data and converting it to some standard format, like some generalized standard format, so you can save it to disk and then recreate that data in a later form, in another form later. One more question, and then we'll get started with this. How would you detect fake news using ML and DL? So guys, we are at a point right now where the tools available to us to generate data are getting better and better. So fake news will get more and more realistic. But at the same time, the classifiers we have to detect what's fake and what's real will get better as well. So it's crazy if you think about it. Viruses will get better at learning to find vulnerabilities in systems. But at the same time, virus detection algorithms will learn to get better at detecting what is trying to attack its system. So it's this battle, it's this constant battle with both sides getting stronger and stronger. And machine learning is at the forefront of it. And the way we make sure the good side wins is by spreading AI. So making sure everybody has access to it. Because if only if you have access to it, then bad things can happen. So learn AI, tell your friends about it, spread AI awareness, tell everybody about it. We gotta get this power distributed to everybody to prevent bad things from happening. So we're moving into a very beautiful world, and we have to make sure that everybody has access to this power. Anyway, so that's it for my rant on that. Now what we're going to do is we're going to visualize what we've just written, and we're going to make sure that it works. So what happened here is to run this. So let's see. Okay, so we want to run this in Tensorboard. What have we done here? We saved it to this log directory right here. So it's in TMP MNIST tutorial, and that's where we saved it, okay? That's where our file writer saved it. So now what we want to do is we want to train our model, right? So let's train this thing. So we'll say, make it bigger. Python, where am I? MNIST.py. And that's going to train the model, hopefully. It will train it so good, so good, so good. Okay, good, so great. So now it's training the model. Okay, so while it's training, and I encourage you guys to train it, it's going to take about 5 to 7 minutes on a CPU. And it's going to take about 5 to 7 minutes on a standard CPU on your laptop. So don't even worry about not training it locally. You could totally train it locally. So while it's training, we're going to run Tensorboard. So to run Tensorboard, now all of you who have TensorFlow will have Tensorboard. There's nothing extra you have to do. So let's initialize Tensorboard. I can do a Q&A live stream someday, but right now we're going to just run Tensorboard. So to run Tensorboard, we run Tensorboard, and then it's, what was it? It's log directory equals, and then the path that we saved the logs to. So what happened is it stopped working 5 minutes before the demo. So I'm going to paste it, and let's see what happened. We're going to debug this together. It's definitely going to throw an error for some reason, which is so annoying, but it is what it is. Come on, baby, let's do this. Okay, so this is what I'm talking about. So normally, this would show the URL that we could then visit in our browser to visualize our TensorFlow computation graph. But instead, it's showing this error, TensorFlow starting Tensorboard B41 on port 606. So I don't know what that is. And so I was Googling this 1 minute before the stream started. But I found that someone else had this issue. Tensorboard isn't showing. And this was not a recent issue. This was a year ago. But he had the same issue, and then Dan Monet, who I interviewed, who is also the guy who's in charge of this stuff on the TensorFlow team, said something, and I'm like, blah, 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 blah. I mean, this thing goes on forever, but what's the result? So this is what I do. I just kind of like zoom through the stuff, and so, okay, so he had debug. So maybe adding a debug flag at the end would help. So let's see what happens here. And guys, if it doesn't work, we're gonna visualize it somehow. We'll figure it out. Okay, so debug. Let's see. Oh no, fuck.
There's your chat right there.
Okay.
You need this right now?
No, it's okay. Okay, so then we could try it again with the debug flag as the GitHub issue says. And okay, so yeah, Ben has a good idea. Let's just open up localhost and see what happens. Localhost. What was it? 606? No, it was 606. Let me pause training here because it's really taking up compute and I don't need that right now. Okay, so something here is loading up. Okay. Yes, okay. Yes, I'm so happy that this is working. Guys, I'm so happy that this is working right now. This is the greatest thing. Who is this guy, Benjamin Schultz Larson. Shout out to you. Wizard of the week, wizard of the live session. Okay, so here's what's up. Let's visualize this. Okay, so where were we? For our scalars, so let's look at the, you know what, let's just go straight into the embedding because that's what I'm most excited to look at. Look at this. You guys who have stuck around get to see this amazing, amazing, amazing visualization. So let's talk about what this is. So what this is these are our embeddings that we generated. So remember, in our fully connected layer, we fed those into our embedding visualizer. Okay, and the way that we are visualizing them is with those sprites. So remember, the sprites are these files, and it's like a matrix. We're cutting it. It's like a matrix of, I don't know, how many are there? There's like 28 by 28 or something like that. But these sprites represent each of these embeddings that we've learned. Okay, so what we're looking at right now is a visualization of this graph, and we're using PCA, Principal Component Analysis, as a technique to map them out. So let's talk about what this is. Okay, so PCA versus TSNE is a good question. So when would we use PCA and when would we use TSNE? So actually, I had my notes on that. So I forgot about that. Thanks. So PCA is a technique that we use to visualize data. And it's actually, most of the time, you'd want to use PCA over TSNE, most of the time. Okay? Most of the time, we'd want to use PCA over TSNE. But in this case, let's look at what TSNE looks like. Boom. Let's find the nearest neighbors using TSNE. And watch it move. Let me make this big. Nope, wrong way. What the hell? Okay. Okay, so you see that they're clustering here. These values are clustering where they're supposed to be. So all the 6s and all the 3s and all the 4s, they're all clustering together. And what we want to do is we want to compute the distances between them. So there's a lot of things that we can do here once we have them visualized. And we're going to talk about what all those things are that we can do once they're visualized. Okay, so there's a lot we can do here. And the idea of SNE and TSNE is to place neighbors close to each other. So that's what this is doing. But the thing is that it almost completely ignores the global structure. But PCA is the opposite. It tries to preserve the global properties, and those are the eigenvectors with high variance, while it may lose, it could lose the low variance deviations between the neighbors. So it's a trade-off. And there's actually a great Stack Overflow link for that in the GitHub, like right at the very top. The Stack Exchange showing like 5 reasons you want to use PCA over TSNE. So that's what that is. So what we can do here is we don't even just have to visualize the we don't have to just visualize the okay, so there's a lot of comments here about my name and stuff. How many people we have here live?
We're at 440.
We have 4. So I'm here to say this to 440 people live. Okay. My name is Suraj Raval. I am Indian. My parents are from India. Let me just say this, okay? When I was 18 years old, I legally changed my name to Jason Scott Ravel when I was 18 years old because I wanted to do great things. And I felt like the only way to do that was to be white, or at least anglicized. It was only 3 years later that I legally changed my name back to Suraj Raval. I learned to love myself over time. I learned to love my identity. And now I am unabashedly Suraj Raval, an Indian and an American. So I just wanted to say that publicly. It's embarrassing to admit, but it gives vulnerability, but it's also a point of, it just needs to be said. It needs to be said to the world. I am Suraj. Yes, my parents are from India, and I love being who I am, okay? So I am very Indian. And I love it. Love Indian food. Love all the Indian culture. Love India. I visited, went there for 6 months. And yeah, I just wanted to say that live. So, where were we? Yeah, a lot of racism growing up in Texas. But anyway, back to this. Back to PCA and TSNE. Where were we? Where were we? So, what are we doing here? Dimensions. So we have 2D versus 3D. So we want to, there's several things that we can do here with our graph. And there's a lot of things happening at once. Let me focus here. OK, where were we? Thanks, guys. I appreciate the support. Anyway. I guess I did want to see the comments and see what people thought. It's one of those things that I haven't really admitted before to a lot of people. But you guys are my homies. You guys are my crew, and I'm just going to continue being real with you guys. I'm going to continue giving you all of me, all of Suraj, every part of me, every part that I've always been afraid to show, whether it be rapping about TSNE or whatever else it is. You have a very unique part about you, and you probably don't even realize this. You have a very special skill set. And if you find a way to encompass all of those things you can do into one activity, you will find success. And that's what I'm here for. I'm here to help you be successful. That is my goal. That is the reason that I do this. I want to help you become awesome, because if you're awesome, then our society will be awesome. This is power unlike anything we've ever seen before. If you're able to understand this stuff, you're going to be amazing, okay? You're going to do great things. So where were we? Suraj, you deserve a plate of biryani. That's my favorite comment of the day. Where were we? I would love some. Okay, so, man, I'm just saying all sorts of things right now. We were somewhere else. We were somewhere else right now. We were talking about TSNE. So we have our tensors and we have our the color map in our labels and our dimensions. Oh, you can change the colors too. So check this out. You can change the colors too. So we can change the color by label. We can, so when we spherize the data, it puts it into a more ball-like structure. And we can also search for different things that we want. So if I can say 7, it's going to show all the 7s. So this can also be used for word vectors. So remember in one of our videos, we talked about the difference between man and woman, like man plus woman equals, well, no. Man plus woman equals child or something like that, but king and queen. That also works in here. And I would love to show you guys that later, but natural language processing later on. So, yes. So 6, 5, 4, 3, 2, 1. That was a countdown to nothing. I was just typing this out. How cool is this though? You could visualize it, and you don't have to just visualize your data. You can also visualize the weights. You can visualize your biases. You can visualize a lot of different things. And in fact, you can visualize stock prices. What I would like to see, and this depends on the TensorFlow team releasing plugins for TensorBoard, is I would like to see more plugins for this. So I'd like to see more people make things for this. So we can choose different components. What else can we do? We can do, oh, night view. That's my stuff right there. And we can also select parts of it. So look at this. So if we select this bounding box selection and we select some specific part of it, we could then get those parts. And then I want to show the cosine distance. So let me show how to do that. So if we were to isolate the points that we've just bounded in a box, we could then find the cosine similarity between those points, which is, so by the way, bookmarks are to share this with other people. So you can download it and share it with other people. Now I want to yeah, sure. So thanks. And we can do custom visualizations as well. We can say like from 3 to take these labels and then match them using some vector use case, a random vector. Anyway, let's talk about the other parts as well, because it's not just this. There's more to it than this. We have 9 minutes to go, right? Is that, or, okay. We have 9 minutes to go. Those last 4 minutes are going to be for questions. Let's talk about these other parts. So the scalars tab is for scalar summaries. Those are single number values that change over time. Okay, and what we have here are the accuracy and the cost function, which is XENT. The x-axis shows the time steps, and the y-axis shows the accuracy or loss. And if we can increase the graph for a closer look by doing this, just like that, or to view a wider range of data points, depending on the, and which expands the y-axis, just like that. Okay? We can also double-click to zoom out. So double-clicking zooms out. So we zoom in, and then double-click to zoom out. Okay? And the step option shows the time steps. Okay? And so a great thing about this is, so right now we only have 2 of these, 2 scalars. But if we had multiple scalars, so if our computation graph was really complex, then we could group them together. So if I type in accuracy, or sorry, if I type in like LOL, it's like, what's going to be here? Nothing. But if I type in accuracy, it then encapsulates the accuracy that we already have. So if we have names like, accuracy / accuracy 1, accuracy / accuracy 2, accuracy / accuracy 3, and then I were to create accuracy right here, it would then encapsulate all of those. Okay, so that's great for doing in the browser encapsulation, similar to namescopes, but kind of like a GUI version of that. Okay, save your question to the end. And then smoothing makes the graph smoother or less smooth. Less smooth is if you want more, the trade-off here is less pretty but more accurate. What else we got? We got relative and then wall. Relative shows the time relative to when it started, whereas wall shows the time of training in general, like in real world time. What else do we have? We have our images. So these are the image summaries that we created. We can visualize them right here, okay? And then we have audio. So I haven't actually seen somebody use audio for TensorBoard. And believe me, I have looked. I have looked on the web and I haven't seen anybody do it. So I would love to see it. I would love to see someone, and I actually, I would love to see someone use WaveNet or one of these things to look at audio. I think Magenta might, but Magenta is so hard to get started. There's so many scripts, and it's very confusing. So let's look at our graph. I can't believe I saved the graph for last. But the thing here is, the graph is, these are our name scopes, right? So these are ConvNet2, Conv1, FC1. These are the name scopes that we created. And if we double click, we can then see the parts that are encapsulated in the name scopes. So why are these colored different colors? So for every color except for gray, those are the default colors. So for every color, TensorFlow automatically looks at the data inside of these operations, and if they're the exact same, then it'll color it the same. So it's kind of it's a way of organizing data so it's cleaner, and it's a way for us to know that it's going to be the same type of data. Okay? And the reason they did this is because in Inception, there was some bug, and it was because in one of the layers, there was like one small difference. So now they have this by default. So colors, it's going to color code itself. And if you look over here at the side, you see this init all by itself. That's because TensorFlow detected, TensorBoard detected that there was one operation that was continuously used a lot. And so then it put it into its own section. Because if we didn't, then it would look crazy. So let me show you this. We could put this init function back into the graph, and then it looks like this, because it's used all over the place. But if we remove from the graph, we could see all of its connections and have the graph be cleaner. So the reason it does this auxiliary node function is to make it cleaner to view. Okay, and then we can also structure it by device, whether that's CPU or GPU, or the structure. And we can look at everything that's inside of the graph like this, and all the layers, and increasingly so much complexity. I love it. I love it. Man, I wish I had time to just make my own project and just make just really go dive in on this. But I'm having so much fun making content right now, so I'm just going to keep going with this. Two more things I want to show really fast are the distributions and the histograms. So the distributions are for the weights, and our biases, they're for layers. Remember, we randomly initialize them, but they change over time, and we want to show what they actually are compared to what they possibly could be. So the possibilities versus the actuality or reality. And one more are the histograms. So histograms are a histogram plot allows you to plot variables from your graph. So if your model has weights, the histogram shows you the values of those weights and how they change with training. So it's this nice little 3D looking graph, which is pretty cool. And yeah, so that's it for this. We've got 3 more minutes for questions. So let me answer some questions, and then we're out of here. Wow, there's even more people in here now than there were before, which is insane. And now there are 432 people here. Okay, so let me see what people. The video did not pause. In deep neural networks, what is an alternative for gradient descent for minimizing errors? In deep for minimizing errors, so that's a great question. There's stochastic gradient descent, which is different from standard gradient descent. There are a bunch of different optimizers. Atograd, Atom. If you look on the TensorFlow documentation for optimizers, you'll find a list of them. Two more questions. Will deep learning solve intelligence? So, spoiler alert, I don't think so. I don't think deep learning will solve intelligence. I think it's a pathway to get there. We need to make more computationally efficient models with that need less data for the same result. And I feel like there's still something that we're just missing, something very fundamental, something very basic. And yeah, but we'll get there. We'll get there. Two more questions, because we have 2 more minutes. How do you explain the evolution of the weights distribution given the evolution of the gradients distribution? So recall, and I have a great video on this, backpropagation in 5 minutes, that the gradients give us a direction to update our weights. So they are, and your question was, it's gone now, but how do we, something about relating the gradients to the weights. So the weights, a great way to model that is to have histograms for both the gradients and the weights. Right now we only have histograms for the weights, so you can see how they both change in real time. One more question, two more. Does our brain use backprop? No, it does not. Our brain does not use backprop. Atom optimizer versus SGD, I would say SGD. And one last question, is LBFGS a true linear regression technique? LBFGS is one of the most complicated things that I've come by, I have to admit. I don't think it's a linear regression technique. Yeah, anyway, yeah. Blesher, what was it? LBFGS was Blesher, Fescher, Gescher, Sescher, or something like that. It was the name of 4 scientists. Anyway, so that's it for this live stream. We got 400 people at the end of a live stream. That's amazing. Thanks, guys, for watching. For now, I've got to go make more technically accurate, more mathematically accurate content for you guys, because I really want to increase the learning capability of my content. So I love you guys. So thanks for watching.